Good morning, good afternoon, and good evening, everyone. We are starting off with the second part of rewriting Git from scratch in Go. Thank you very much, everyone, for joining. Whoever is joining and watching this series, I hope you are learning from it. I know that I'm enjoying it, and I'm enjoying the preparation work for these series, because it's a fun topic and it's a challenging topic and it's a very interesting topic all the same time. Now, if you didn't watch part one, stop here, go watch it on YouTube, and then come back. Because as much as I would love to make this video series, each video to be as independent as possible from the others, it's not really possible, because this is a topic that we need to build on top of the lessons learned from the previous steps, so that we can always make progress, and we cannot really start from scratch every single time. It's just too difficult, and then it's really gonna stretch each episode to endless hours, and we really don't have the luxury of that much time. Now, as a quick reminder, this series is based on the book Building Git by James Coughlin. Actually, while we say this, let me switch to the view where I'm sharing my screen, because I'm pretty sure you're not here to see my face. This is the code. Let's move to the browser. All right, awesome. So the book I'm talking about is Building Git by James Coughlin. You can just hop on his website and buy yourself a copy. I like to promote this book because, in my opinion, this video series would not have happened without this awesome reference. This is the reference that this series is based on top of, and what we're using as our foundation. So if you want to follow along, you can read this. I'm doing the implementation in Go. However, this book is written using Ruby. Things will definitely change, but the fundamentals are the same. Now, in today's episode, we're gonna be continuing. We're gonna continue building from where we left off last time. Today, we're gonna be finishing the implementation of Git commit, at least a basic implementation of Git commit. We're gonna be building the Git database, and the best part of it all is that at the end of this part, we're gonna be able to commit our code, that we've written for Git in our version. So we're gonna be using G, what I decided to call my version of Git. We're gonna use G to commit G, which is gonna be pretty awesome. And I think this is what Linus did when he did the implementation for Git. He used the tool to commit, to check in the, well, not necessarily itself. I'm not sure if he did it for the Git code itself, but he did it for the kernel. Now, I was hoping for one more thing to happen today, which is it's a nuance that I would like to clarify. And a lot of the other tutorials on building Git and things like that I saw, they are building a version of Git, or like sort of creating something new. However, what we're doing in this series, we are literally re-implementing Git. So our code, our objects that are going to be stored in our whatever metadata folder we choose to name, and whatever you choose to name the tool and whatnot, if you rename that folder to .git, you should be able to use the rest of the Git tools, because Git is not just one tool, it's a toolbox, like git log, for example, or git show, to engage with the objects that we are writing on disk. Okay, this is a very important distinction. So we are literally re-implementing something that is compatible with the Git toolbox that exists already. And hopefully by the end of our implementation, we will have something as close as possible to the real Git. All right, perfect. Last things I want to mention. Do not be shy. The reason why I'm doing these as a live stream as opposed to structured video content is because I want to engage with you. I know live streams are more demanding than regular videos, because in regular videos you can just skip and move forward and you can control the time and whatnot. However, I want to receive your questions. I want to answer them live. I want to be able to provide you with more information that sometimes maybe I forget to talk about. Or if there are things that you need more clarifications on, I would love to develop those a little bit further. So I would like to make this a back and forth as opposed to being a monologue of me talking for an hour and a half. There are no silly questions, so just fire away whatever comes to mind. I would love to clarify these things. A couple of last things. Join my Discord server for just a couple of reasons. One, I make much more content available on Discord server, like thoughts of the day. We engage in different conversations. I share some advice, tips. We discuss some of the more up-to-date stuff that I'm not able to put in a video format. Being on that server will get you access, to the latest and greatest that I'm able to produce, and we can engage together also, not necessarily through videos, but directly on the server. So this is a great opportunity for you to join and, be part of our small community. Hey, Adib, thank you for joining. I'm happy to see you here. And of course, don't forget to subscribe to this channel. Last thing I want to mention before we start writing the code. This is the repository for my implementation of Git. However, it's only going to be available for, it's a private repository, as you can see. It's only going to be available for YouTube channel members and Patreon subscribers. So if you would like access to this repository and the code base to keep it as a reference, maybe to fork it, to do whatever you want with it, subscribe. This will help me continue building my content. It will help me invest in more tooling, and also it help me invest in spending justify spending the time on creating all of this awesome content for your entertainment and educational purposes only. All right, I talked a lot. I see already a few folks who have joined. I would put, yes, Hadi, I would put the Discord server link. Actually, it's not that difficult. So if you go to glich.stream, the thing is that people don't understand about this link. If you just go to glich.stream, and glich is Glich without the T. I thought it would be funny to write it like that. Anyway, so it was stupid. But the idea is, if you just go there, you have everything. You have the links to the knowledge graph. You have the link to join the Discord server. You have the link for Patreon, for tips, for YouTube, for my podcast, for Twitch, for TikTok. You can even hire me as an advisor. You can also book one-on-one coaching sessions with me. These are career related or whatever agenda you want to define. You can book these sessions, talk to me. I would love to share my insights with you. So again, glich.stream, and you will have all of the links that you need in one place. Brilliant. Okay, enough talking. Let's get started. Let me open up my VS Code. And this is where we left off last time. Last time we talked about how Git represents files on disk and how things are stored. We talked about the content of these files. I showed you also how you can write a small tool that does a decompression of these files so that you can read them because they're in binary format and they are compressed with zlib-deflate. And I showed you how you can decompress them to see their content. We did a basic implementation of git init over here. I showed you how you can also start writing the CLI tool using Cobra. We did a small implementation of git init, which is going to create pretty much the objects and the refs folders, as well as our metadata directory, which we're going to call, in our case, .g instead of .git. You can rename it to whatever you want. We call these, we declare these as constants because, they're not really going to change in our implementation. You can change it in your own implementation later. So this is what git init does, and then we started the implementation of git commit, but we didn't go far with it. So we started by creating the internal database. The database is going to help us store objects on disk, and it's going to be the abstraction that's going to handle a lot of that stuff. So today we're going to continue working on this database. We're going to create all of the structs that we're going to need to execute a proper git commit. And hopefully, if we have enough time, we're going to be able to chain commits together so that we have, sort of a linked list of commits. and we're gonna start on the tree implementation. Now, the tree implementation is gonna be interesting because it's gonna be very basic right now. It's gonna be just linear, where commits are gonna link to each other. However, in the future, maybe part 3, maybe part 4, I will see, we're gonna do a full-blown implementation of a Merkle tree. And we're gonna be able to also commit not only just the root directory of our project like we're gonna be doing today, we're gonna be able also to commit all of the subdirectories and all of their content, and manage those, because right now we're not doing this, and I just want us to get to a working copy or a working version of this as soon as possible, and then we can start adding all of the different tricky stuff and expand on it, because that's what you also need to do in your projects. Get to a working state as soon as you can. At the end of each programming session you do when you're doing a side project, make sure that it is in a working state and don't leave it broken, because this will give you like sort of the incentive to come back in later and work on it. I want to ask you a small question. Is the font okay? Is the text okay, or do I need to zoom in? If you can give me a signal in the chat, that would be awesome. Otherwise, I'm gonna assume this is fine. So please do let me know. All right, so where are we gonna start with this? Let's go back to our git commit, and first of all, let's make sure that we are actually able to build our project. What we're doing here is we're just building the main.go file, and then we are outputting it as G. All right, a little bit more is great, so let's zoom in one more time. Yeah, I think this should be fine. I hope it's okay like this. I'm gonna keep an eye on the chat. Also let me know if this is okay or you need me to zoom in a little bit. All right, cool. So we're just gonna make sure we're gonna build it just to make sure that we are in a good state, and then we can proceed. The second thing I want to mention is I'm gonna try to implement unit tests, but I'm not gonna be able to implement it all because it's gonna take much more time. So what I would recommend that you do in your own implementation is to implement as much tests as possible, because believe me, things can get complex really fast, and if you don't have tests, you're gonna have a difficult time. All right, so if we run our tool, as you can see here, we will get the default message. All of this stuff is customizable, but I'm not gonna spend time on it because that's the easy part. You can do that yourselves later on, and change all of these messages and make sure things work whichever way you want them to work. All right, so what are we doing in our git commit? The first thing we want to do is we want to fetch the current directory. Why? Because whenever we are making a commit, we are making it in whichever directory we are working in. Obviously, later on, we can expand this to handle different directories, but for now, we're just gonna limit ourselves to this. And as you can see here, Copilot is already doing much of the work for me, which is always awesome, just because I don't like doing the boring stuff, because this is simple, right? I mean, you know this stuff already. We don't really need to spend a lot of effort on this and really explain what's happening. So we're fetching the current directory with the OS part of the standard library, and that's it. Go will handle it. It will handle it across different operating systems, and that's the easy part. The second thing we want to do is we want to create the path for our git. I'm not gonna call it git because my implementation is g, so for our git directory. And again, I have a very bad habit of choosing very bad names, but anyway, so what are we doing here? We are concatenating a slice of the root directory which we fetched over here, along with our where did we define this constant? Did we define it here? Yes, this needs to be moved actually. I don't like this at all over here because we're gonna use it right now, but we're gonna probably refactor it in a little bit. So because we defined our the name of our directory as a constant, we need to use it over here. Then we don't use the / because we want an actual separator that works across operating systems. You don't want to define this constant yourself. You want to use whatever Go provides you with. So Go is going to provide you with the rune that is going to act as a path separator, because in Linux it's a /, in Windows it's a \, and things might differ in different places. That's why I also like Go, because it can handle this type of stuff. Now, the second thing we want is the database directory. And if you watched part 1, you will notice that we talked a lot about the .git /objects folder. And that objects folder is the disk, is whatever we're keeping on disk for, we're storing all of the objects that we're tracking, like the blobs, the trees, the commits on disk inside the objects folder. This is the most important folder of our implementation, and we're going to be using it right now to store what we're going to call our database. And this is where all of the files that we're going to be creating are going to be stored. All right, cool. So now that we have the metadata directory as well as the database directory, we're going to proceed to create a new database, which we already did over here. Okay, calm down, Copilot. And instead of creating a new database, because the new also takes a path, right? So instead of creating a new database with a mock string, we're just going to pass the database directory over here. And this is how we're going to be initializing it. All right, so here I want to change things a little bit, because we're not going to be returning any reference over here, so we can use this pattern. And what this does is you can do assignment in Go, right, over here inside the conditional. This is not something familiar in other languages, but it's a nice thing in Go. You can call this function, and then this function, as you can see here, it returns an error type. And then we can assign that error to our variable over here. And then we can check if this variable is not null, or nil in this case. And then if it is nil, then we spit out an error and we exit, because we don't want to continue. So we're going to say here, failed to create a new database object, or a new database. Actually, this is more, this is better. Then we're going to separate this with a dash, and the view over here is going to spit out the value of this error, actually object over here. And yeah, it's going to show it to us in the terminal. I have to apologize. I'm not keeping an eye on the chat. So I'm not keeping an eye on the chat. So I will just, it's not my priority today, just because I want to try to get as much code done as possible. So I apologize for this, but I'm going to drop an eye every once in a while to it. Okay, cool. Someone mentioned that path join is an option. Yes, definitely it is an option, which can be used over here. Feel free to do as much refactoring as you'd like in your own implementation. Now, let's fix this. So we have inside the internals package our database.co file, which we created last time. Why am I separating those? Because I think it's better to have the objects inside their own separate package. These are internal implementation objects. They don't need to be part of our command package. This is how you can structure your Go projects, which is pretty nice. Make sure that the package contains exactly the stuff that are relevant to it, and everything else can go somewhere else. All right, as you can see here, we have in the database also something not necessarily great. We re-implemented the constants, because this is a different package, and whenever you create constants, you create them, you know, they are available in one package. So what I would like to do is also start with a small refactor of this, and let me clean it up, because let's clean it up this way. Let's clean it up by creating a new file, and let's call this file constant oops, sorry, let me save it. Constants.go, and we're gonna put it inside the package internals, and this is where we're gonna define these constants. So let me move this out because I already had a to-do to clean this up before, and let's remove this. And I think these are the constants that we need for now. Let us also do one small bit of a cleanup. Here we already have this definition, so I'm gonna remove them. And then I'm gonna have a bunch of errors, so let's address that. We can just say internals dot this. Why? Because if you hover and click, it will take you to the package internals where we define these constants, and this will be the one location where we define these, and that will be much better and cleaner implementation. Let's fix all of this stuff over here. All right, cool. Do we have any more issues? Let's see. What is it complaining about here? Oh yeah, this one. Let's fix it. Use all of the tools at your disposal. Okay, we're gonna clean this up in a bit. So that's the first refactor we did today. The second thing I want to do, which is, I don't want to keep jumping context, but let me just do this very quickly, because before I forget, I'm going to be building this project a lot. I'm going to be probably running the tests and, you know, running some sample runs a lot. So I'm going to be using a Makefile. And I'm not sure if you're familiar with Makefile. Is sort of a you can define it once. You can define targets and you know, targets and files, and you can define the commands you want to execute whenever you want to build a certain target or whenever you want to execute a certain target. And Makefiles are great for this. So let me write it very quickly before we move on. Default goal is all. Project name. Do I have to define something? Let's call it g, and then we have the binary name. This is how you define variables. So we're gonna call it g or g, and then we're gonna save this as our Makefile, and we're gonna put it inside the g folder. All right, awesome. The next thing we're gonna be doing here is we're gonna define phony all clean test rich. This is for unit tests to run them, and then let me put this one here. What else are we gonna have? Run, build, and help. And then all will basically trigger the clean, which will clean up our directory from our previous build executable binaries. And then we're gonna build and test. So basically what we're saying here is whenever we call all, we're gonna clean up, then we're gonna build, then we're gonna test. But we didn't really define what these targets are. So here Copilot is chiming in and doing stuff for us. Let's start by, yeah, I think I like this. Echo, and then go clean, we don't need this one, and then rm-f binary. I think this is enough to clean up. Also, let's do something true, because if the binary doesn't exist, I want it to also pass. I don't want to fail if the binary doesn't exist, because the cleanup should always, if there's something to do, it should be done. If there's nothing to do, let's skip it. So running tests is not necessary, so let's just run this because we don't need to be that verbose. And then actually the terminology rich here, I don't like it, so let's say test verbose. And then what I want to say is build, which is what I'm going to be using most of the time. Go build -o, and then the binary name, and then v. What I want to do is I want to wrap this with double quotes just so that we don't have issues. and then this should be main.go. And then what I want to do is I want to make this executable. There we go. One last change over here. Now let's test the Makefile very quickly. We can say make. Also, you need to install make, huh? So we can say make test. Great. Oh, sorry, my bad. This already wraps my variables, so we don't need these double quotes because you can see here, right? They're already wrapped, so that's good. Now make test. We ran the tests because we don't have any tests. Nothing is gonna happen. That's great. Make clean. Let's see what happens here. Okay, G was removed, and then make build. Perfect. So we have the, if you look here, we have the G that was created, the binary, and then it was made executable. You can see it from the X that was added over here in the file mode. So we have a basic Makefile right now, which we are going to be using pretty much all the time. All right, cool. So we cleaned up the constants. We created our Makefile. Now let us move on to the database implementation. All right, so we don't really need to change much over here because we have path already defined, part of the struct, and we are just passing that path that we pass as a parameter to this variable. Over here, we need to implement the storage method, right? So this is how we're going to be storing the blobs on disk. Now, this is where things get a little bit more complicated today. So what are we gonna pass to store so that it can, store it on disk? We need to define a new interface, and this is the new interface, which I'm gonna call the object interface. Why? Because everything we're gonna be doing, everything we're gonna be creating as structs, like blobs, trees, commits, whatever, all of these are objects. So we're gonna define this interface over here because I want to be able to be safe. So whenever I tell my method store and I pass the type object, or I pass the interface, any object that doesn't implement that interface will not be stored. The compiler is gonna complain about it, and we're gonna be safer this way. It's much better. So let's define it. Object interface over here, and it's an interface. And again, forgive me if I'm messing up some of the best practices. I'm not necessarily a Git expert, a Go expert. I'm also doing this because I am learning a little bit Go as I go. And then this helps me. Let's put it this way. The best way for you to learn is to build something, right? Be it a language, be it a tool, be it whatever it is, just build it. I don't need the type, I just need the set ID. Now you will ask me, why are we having these setter and getter method type stuff over here? Trust me, we're gonna need them. You will see in a bit. Believe me. Just trust me on this one. We're not gonna be able to export the variables so that they can be defined from elsewhere. All right, so now that we defined the object interface, we can proceed to start defining some of the basic objects. And to show you how we can use it, we can just say here object and then object interface. Then every time we pass an object that implements object interface, we're gonna be able to store it. If we pass something else, compiler is gonna complain. We're not gonna be able to move forward with this. Now, in order to make the storage more concrete, we're gonna need to start defining some of our basic objects, right? And the first one we're gonna define is gonna be the blob. Let us create a new file over here. We're gonna call it blob.go. Sorry, my muscle memory always calls stuff blog for some reason. And again, we're gonna be doing a lot of boilerplate today, so stay with me. Again, package internals, we're gonna define a type blob, which is a struct. And then you're gonna notice that all of these objects are gonna have the similar structure. First of all, we're gonna have the object ID, which is gonna be the SHA. The SHA is gonna be generated from the content of the blob, and each blob will represent pretty much a file in our project. Any file that we have that we're gonna stage and commit. We're not gonna stage now, we're just gonna commit for simplicity's sake, is gonna be a blob. And then we're gonna read that file's content into memory. We're gonna create a SHA-1 from that content, and then we're gonna sort of store that blob on disk in the representation that is similar to how Git does it, so that our implementation is also compatible with Git. And inside the blob, obviously, we're gonna have the data, right? The data is gonna be the content of the file. Now, the compiler is complaining that we didn't really implement or we're not really using these variables, so let's start using them. First of all, we're gonna define this method that's gonna belong to this structure. And this is how you do methods in Go, because there are no classes, right? So this is the don't think in classes in Go. Don't think about classes and you know, inheritance in the normal way. Go is designed to be a very minimalistic, simplistic language, and that is the reason why it's loved by a lot of folks, because it doesn't have all of these nasty abstractions that are not necessary at all. Once you start writing simpler code, you're gonna start realizing that a lot of these abstractions that are in other languages are not necessarily needed all of the time. They have their use cases, but they're not always needed. All right, so let's finish the basic functions we need. And remember, right, what are we doing here? We are implementing the object interface. So we have the toString, getOID, and setOID. And you notice Copilot, how did it know that I need to implement these functions? Because you know, it recognized the interface and it's sort of suggesting based on that. So before I implement the toString, let's implement the getOID, and here I'm just returning the byte array or byte slice. And then we have the setOID, which basically takes an OID as a parameter and just sets it. You're already familiar with all of that stuff. And finally, we have the toString implementation. For now, we're just gonna return the data, which is a slice of bytes, and then we're gonna return the string representation of that data. Obviously, it can happen elsewhere, but because the method is called toString, right? So we do it here. And that means that blob is now has implemented the object interface. And then if we say in here, for example, in the commit.go, if I say something like, hold on, we're gonna get to it. We're gonna get to it, Copilot. So if I say something like db.store, and then like I pass a blob, it shouldn't complain. Of course, we didn't finish the implementation here. Probably, you know, maybe this. Wait, just very quickly, let's do it this way. And then if I say, oh, 1 second. See, that's the nice thing about Go. When you define the interface, the compiler recognizes it and starts complaining about it. So we cannot, it's not allowing me to pass blob to store, because it says that internals.blob does not implement the internals.object interface. Method go getOID has pointer receiver. Let's see what's happening in our implementation. That should work. Why are you complaining about it? Oh, sorry. Okay. Yes. Okay. Perfect. So now that we have another error, we can just say here, fine. What's the complaint now? That's the nice thing about Go. You know, just like before even running it, you just get all of the different problems. Let's see. Can Copilot solve it for us? Oh, I already defined error. Sorry. Yes. Thank you very much. I already got it. So I already, not here. I've already done it here. Right? This is the first assignment. So here I cannot really recreate the variable. My bad. I always fall into this trap. All right. I see a lot of questions in the chat. Let me just see. Where's the implementation declaration for the interface? So this is the object interface right over here. And you don't have to say in Go that you, with Go, as long as you implement the methods, right? As long as there's a struct that has the methods of the interface implemented, which are in this case here, that's it. Go recognizes that this is an implementation of the interface. You don't have to explicitly say that in like other languages. Okay, so that's the nice thing about Go in general. All right, now we have a blob that's implemented. Let's actually use that and continue our store implementation. We are in the database right now, and we're gonna store that blob. We're gonna try to store that blob on disk, right? And as you remember from previous part, there's a very specific way with which we store blobs on the disk, because we need to write that file in a very specific format, which is going to be implemented in this function over here. So the first things first we're going to be doing is, if you remember, I need first of all, the start of the blob file needs to be blob, and then the size of the object in bytes, and then I will have a null byte, and then I will have the content of the blob compressed using zlibdeflate. Okay, so that's what we want to implement in this store method over here. So let's do that. First of all, I will need something called a variable called encoded data, which is also going to be a bytes buffer. We're going to see why in a bit. And then what we're going to do is we're going to create a bytes slice with the following format. Right? It's going to be the type, and then the size, null byte, and then the data. Right? And this applies to the blob, it applies to the tree, it applies to the commit, it applies to pretty much anything we want. Right? So we're gonna say the following: data equals byte format dot printf, the type of the object. That's how we do it. And then we're gonna say the size /x00, which is the null byte array, and that's it for now. And then we're gonna pass we're gonna replace it. So this is the object, which is gonna be the blob in this case. We're just gonna have a slice of the type, and then the size, and then a null byte array. And then the size, we're gonna get it by just simply, getting the length of the object.toString. Second thing we're gonna do is we're gonna try to append to this slice the data. Let's do it like this. And then what we're gonna do, we're gonna try to encode this data using the ASCII 8-bit format. So basically it's big endian, and we're gonna say binary.write. We're gonna pass encoded data, and then we're gonna say binary.bigendian, and then let's see if this is correct. Yes. Why? Because this is the encoding that we're going to be needing on the disk. And then what we're going to do is we're going to create a SHA-1 hash of the encoded data, right? And the way we do it is not like this. We're going to call this object ID, and we're going to be using the SHA-1.sum, and then we're going to pass the bytes slice of our encoded data bytes buffer, right? Remember, we defined it here. Then what we did is we encoded the data, which is still here as a byte slice. We encoded it as a big endian, and then we stored that in our encoded data over here. And what we're doing here is we're just fetching the bytes of our encoded data bytes buffer, or from our bytes buffer, and then we're going to create the SHA-1 hash from that content. The next thing we're going to do, because remember we defined the setter, so we created the setter for the blob to set the object ID. We're going to call it over here, and then we're going to pass the object ID, as you can see over here. What this will do also, just to be very clear, the SHA-1.sum returns a slice that has a size of 20. So 20 bytes. Basically, the SHA-1 is 40 characters, 40 strings, right? Now, that's what you need to remember from your computer science classes. So 40 strings, each character, or each hexadecimal character, right, is going to be represented as 2 bytes. So this is what we're doing right here. We are converting this 20 bytes slice into an unlimited size slice over here, and then we're gonna pass it to set object ID. So this is a small trickery. That's not really a big deal, but let's add a comment over here, just because like some people might get confused by what's happening over here, and the comment will definitely help out. I'm not gonna print out anything, and what I'm gonna do here is I'm gonna define another function. Let's return nil for now, just because it's not done yet. We didn't write this on disk, right? So what we want to do right now is we want to write this encoded data on our disk, and we also need to compress it, right? Because as you remember, we need to compress stuff. So db database, no, not get path. This one is gonna be called write object, and then what it's gonna take is an OID as a byte slice, and the data also as a byte slice, and it's gonna return an error if there's an error. Now, what is gonna happen over here? First things first, we're gonna get so the OID is passed as a bytes slice, okay? And believe me, I will try to make this clear in a bit. I know it might be a bit confusing for now, just follow along. And then once we build this and use it, you're gonna be able to see the files on disk, how they are, and you'll understand this implementation in a little bit more detail. So we're gonna get the hexadecimal representation of OID, and we're gonna store it in the variable OID hex, okay? The second thing we need is, where are we gonna store this stuff? So we need to create the path where we're gonna be storing our objects. And if you remember from the previous episode, in part 1, we discussed that Git, when it stores its objects, it stores them, once it creates the SHA-1, it creates a directory. So .git/objects, and then it uses the first 2 digits from the hexadecimal number, right, as the folder. So let's say we have a SHA-1 that was created that looks like A1, F2, C4, whatever. Go on, Copilot, thank you. What's gonna happen here is that the first 2 digits are gonna be the directory, and then the remainder is gonna be the file name, where the content of the blob, or the object in general is going to be stored. And this is the path that we need to build right now, right? So object dir is going to be, is not going to be this, it's going to be this part over here. So let's construct it together. Strings.join, and again, you can use OS path join, which will work the same, pretty much the same way. And what's happening here is we are getting the path that we stored already when we created the database, right? You remember we have path, we stored the path over here. So we're just going to retrieve its value. And then we're going to get only the first 2 character or digits from the hexadecimal representation of our object ID, or pretty much our SHA. And then we're going to fill it up, or, you know, combine these with the separator. So we're going to have object dir is going to look like this. Then the second thing we need is the object path. And the difference between directory and path is directory is pretty much the folder that contains our content. The path is the full reference to the file, right? It could also be a reference to it's a reference for a file. It could also be a symlink. All right, now what are we going to do? We're going to join this object dir, right? So we're going to take this value over here, and then we're going to append to it the remainder. So this part, this segment over here, to the path. And then also we're going to add a separator. This applies to all of the objects. That's why we also have an interface that we defined. Because we like the consistency, and it creates a safe environment for us to pass something that is compatible all the time. And if it's not, the compiler will complain. Now, sometimes the object path, not sometimes, naturally, if we don't have 2 hashes that start with the same 2 digits, we're going to need to create that folder, right? So we assume that git init has created already .git/objects for us. Great. But the rest, we need to create it ourselves. So this is what we're going to be doing here. We're going to create the object path and all its parents in case they don't exist. So we're going to do if error and make dir all. Make a directory all will create the path. So if for some reason git init fails to create the .git/objects, this is going to do it for us. And what we're going to be passing also here is the mode of the file mode. And we already defined this as a constant, right? So if we go over here, you can see that the file mode, and we're using 0744. I'm going to explain what this means right now in a bit. As our default permission for every single file we create. Git by default uses 0644, but I'm going to use elevated permissions for a bit, just for ease of use at the moment. So let's create a test file. I just want to show you what I mean by mode. So if I do ls-lha, you will see the test file here. And this is the representation. The first bit over here means if it's either a directory or a file, regular file. So you can see here, D means directory. So CMD is a directory, internals is directory. You can see it over here. The first 3 letters over here represent the owner permissions. Read, write, execute, RWX. The second one is for the group, and the third one is for everyone. So, and this is what the octal number over here represents. Okay, 777 is the highest number you can have because it's octal. So the octal means 8, starting from 0. 7 is the last digit. 777 means RWX are all flagged. 4 means it's read without the write, without the executable. There's a formula for this, which I forgot right now, but we can ask Copilot about it, and it will tell us how we can deduce the ASCII representation from octal file mode. Let's do that, actually. Why not? I don't have this in memory because I rarely calculate this. You can reverse engineer it, obviously. So how can I convert an octal value of 744, or let's say 0744, to the file mode, to the ASCII representation of the file mode. And it's going to explain to us right now how we can achieve this and what is the method that is used to do this. Let's see. Interesting. So it thought I meant how can I do it in Go. Because it inferred sort of the context from my environment. It's not, that doesn't work. So how can I convert the oct? All right, let me see the comments. Oh, come on. I don't need this. All right, convert octal file mode to ASCII. I should have these. I should have references for these, for this stuff. Come on. The Red Hat folks must have something. Okay, we talked about this. Now how can I convert? All right, okay, cool. Yeah. So perfect. So read has a value of 4 in octal, right? W has a value of 2, and execute has a value of 1. If we want to have a file mode of read, write, execute for either the owner, the group, or the everyone, we can combine these. So we can say read, write, 4 plus 2 is 6. If we want read, write, execute, it should be 7, 4 plus 2 plus 1. If we want read only, it's 4. And if we want write and execute only, it's probably 3. Right? So this gives us a nice combination that doesn't sort of clash. So if I say over here, I want chmode, let's say 0733 for the file test. Let's see, will that work? What do I get? Perfect. So we get read, write, execute. This is the 7. And then write and execute. These are the 3s. Okay. If I change this to say chmode 0722, right? What do I get? Write only. And then if I change this to 0711, oh, what do I get? Execute only for the group and everyone. Okay, and this applies to pretty much everything. So this is how you can this is how you can understand it. So keep this in mind. Read is 4, write is 2, and then execute is 1. So in this case, the owner can do everything, and then everyone else, the group and everyone else can just read and write. Can read only, actually. Sorry, not even write. Excellent. So let's replace this constant over here with g default permission. and let us continue our implementation. We still have a long way to go. So let's try to ramp up. All right, so now that we created all of the different directories that we need, we're gonna need to do a small trick over here. Whenever you wanna write a file on disk, you cannot assume that no one else is gonna access that file. And in order to make sure that your file that you're writing is never interrupted, first write the file in a temporary directory, in a temporary location, and then when you're done writing on disk, move that file. This way, if you're implementing concurrency, for example, in your application where some other part of the code is trying to also write to the same file, right? Or there's a conflict of some kind, or maybe you're writing and then something else needs to read from that file, the move operation is so much faster, because on the operating system level is just changing a reference, just changing, where that file in the tree belongs. But the write process, writing on this, could be quite extensive, especially if the blob is quite big or the tree is quite big, right? So write in a temporary location that is not accessible to other parts of your application. Once the writing is done, you move the file. This is the best way to handle this. And if you write it to the temporary folder, whenever someone reboots the machine, that storage is gone if you're, worried about cleanup and stuff like that. So first things first, we're gonna get a temporary directory compatible with the underlying operating system. Why? Because not all the operating systems have the same /temp. So in Linux and Mac we have that, but in Windows obviously not. And we're gonna call this temp.dir, and we're gonna call os.temp.dir, which is gonna give us a reference to a temporary folder which we can use. Then we're gonna be creating the temporary file, and then we're gonna be creating a temporary file. However, in order to create the temporary file, I'm gonna need a name for that file, right? So we already have the directory, but we don't have the file name. So let me create a function over here. Let me comment this out. And the function is gonna be generate temporary file name. Come on, compile it. I think it's easier for me to just say yes to compile it and then delete stuff instead of skipping it myself. Anyway, we're gonna pass the OID in a hex format as a string, and then we're gonna return a string as well. And then what we're gonna do is we're gonna return a file, and that file is gonna have the format temp object. You can call it whatever you want, doesn't really matter over here. And then we're gonna spit out the first 3 bytes of our hex hash, or hex decimals, not bytes. First, yes, correct. First 3 bytes over here, which is gonna be the first 6 digits from our hex representation, right? Each digit is 2 bytes. Remember that. Keep that in mind, because it's gonna be. So let's assume the OID or object ID in hex is this. We're gonna return these: A1, F2, C4, B5. How many are those? 1, 2, 3, 4, 5, 6. That's what the file name is gonna be, temp object. And you can verify this in a little bit once we write the files, right? That's how it's gonna look like, and then we're gonna use it over here. So we fetch the temp directory, and then we're gonna create the temporary file. Yes, that's it. And it already recognized that I want to create a temporary file in the temporary directory. If you see here, it just takes the directory as the first part, and then the pattern that's going to be used as the file name. And then if we have an error, obviously we want to return it. Why? Because we're not really dealing with errors over here. We're just returning it for whoever's calling the method write object. Next step is the compression. We're going to compress the data. We're going to compress the data with zlib_deflate. Thank you very much for subscribing, Muhammad. Welcome to the members channel. All right. Sorry, I got a bit startled by the unexpected audio. I always forget to lower the volume. Cool. So we're going to compress the data with zlib_deflate, as I told you in part 1. And the nice thing also about zlib is just like it's pretty much everywhere. Like even here, we can just simply call zlib, and we're going to define a new writer. And then what we're going to do is we're going to pass a reference to the compressed. We didn't define, 1 second. So we're going to define, first of all, a variable called compressed data. And then we're going to, it's going to be a bytes buffer. Then we're going to pass a reference to compressed data over here to zlib. And then we're going to say write our data to this bytes buffer. What zlib is going to do is going to take this reference, it's going to compress the data, and then it's going to write it to our buffer, which we're going to be using. Don't forget to close the writer. Otherwise, you're going to have memory leaks and endless suffering and pain. Next, we're going to write the data to the temporary file. Sorry, I'm rushing a little bit, but I really want to get this part done so that we can show you some stuff, right? We've been writing code for a while now, but we haven't really tested anything. So temp file dot write. We're writing this content to our temporary file, and this is the way we do it. We are simply getting the temp file, which is also a file over here. Thank you very much, Marwan, for joining, and I really appreciate your support. Thank you for this. Please make sure that after you join, I'm going to create a post, and I'm going to send it to only to the members so that you can give me your GitHub handle, or maybe even drop it in the chat over here so that I can add you as collaborators and give you access to the repository of this project. Thank you very much for your support again. I love it. All right. So we're going to be creating the file over here, which is going to contain the bytes array, which is also the compressed object, right? Which is what we did. And then also don't forget to close this file once you're finished writing it. So again, we're writing to the temporary file yet, huh? So we didn't finish. The last step, what we're going to do is we're going to move this file once we're done with the writing. And remember, writing operations over here are blocking. So we're not really writing using another thread or anything like that. So this code is just going to execute in a sequence, and we're not really going to have worries. We can just close it over here and we're done. The last part, I love Copilot just does everything. You see, like I'm barely writing any code, and Copilot is pretty much doing all of the hard work for me. We just simply call os.rename, and we rename the, we just fetch the name of the temporary file, which we created, and now the temporary file contains our data, and then we give it the new name, which is what our object path, which we constructed at the beginning of our function. And our object path is going to be pretty much this. Let's just put it here so that we can keep it as a reference for us. This is what I mean by good comments, right? Like good comments give us allows us to read code and understand it a little bit more easily. Thank you, Muhammad, for subscribing. I really appreciate it. Cool. So good comments are comments that explain and make reading the code easier, right? So you can see here, instead of me trying to figure out, wow, what is the value of this? And then I want to try to remember what does this one do? I can just come here and read the comment, and that's it, right? I understand immediately what the value of this is. And probably better yet is just if I drop it over here, just to be a little bit more concrete. Let's drop it over here and go the linter, sorry, the formatter will fix it for me. And let's put this one over here. You know, this is just cleaner. You can read it. It's easy to understand. the code here. I mean, this is a little bit a bit over the top, but I'm doing it just because I want Copilot sort of to, you know, give me the proper suggestions, and this is what's really happening over here. All right, now I see a couple of complaints. Let's see what's happening. So, okay, Copilot made a mistake or not? Is it? No. Why is it complaining over here? Okay, that's a weird one. I'm already using it. What do you mean it's not being used? Let's see. Oh, okay. Got it. Sorry. We didn't finish the first part. So we need to call this over here. db.writeObject, and then what are we passing? We are passing both the OID, object ID, as well as the encoded data bytes slice. And I think this finishes our implementation for the database. So the database right now, we can initialize it like this. We pass an object that implements the object interface to our method store, which is exported, which means that we can call this method from other places in the package. What this method is going to do is, again, it's going to construct our data. It's going to encode the data into the format we want, which is big endian. It's going to create a SHA-1 from the content or from this data, and then it's going to write this object on disk, and it's going to create the necessary files and folders, and then we're going to create the temporary file where we're going to store the content. And once we're done compressing it and storing the content on disk, we're going to move it to its proper location. Sorry, I need to optimize this a little bit because it's a bit annoying. It's not how it should be. We can do this. Okay, why? Because, you know, if this errors, then we return the error from this one. That's it. Awesome. Let's see. Can we build? Let me remove the test file because we created it. We don't need it anymore. So let's say make build, and that's it. It builds. Does it run? It runs. Perfect. Does it do anything? No, because we didn't finish our commit implementation, right? So we come back here. We created our database. We created an empty blob, and then we try to store this blob. However, oops, sorry, my bad. Where am I going? However, this blob should contain something. So let's make sure that it does contain something. Okay? All right, so how do we make sure that our blobs contain stuff? What we're gonna do is whenever we commit, okay, we are gonna get the list of all of the files in our current directory. You remember, we fetched the root directory, which is our current directory. We're gonna get all the files in the root directory in this case, and then we're gonna create a blob for each of these files, and then we're gonna call the database.store to create an object for all of these files. This is how Git does it. And we're gonna do the same. We're gonna skip the staging. So we're gonna immediately, whenever we call git commit, we're gonna do this exercise. So let us do it together, and let's see if our implementation of the database will actually work this time. All right, how do we do this? Get the list of all the files in the root directory. And thank you very much, Copilot. Nope. Actually, not thank you, Copilot, because this is not correct. We are gonna call os read directory, and then we're gonna pass the root directory. This is how it's done. And then files will be a slice of fs.dir entry, and each of these entries represents either a regular file or a directory. And we're gonna filter them in a little bit. But first, let's make sure there are no errors. Be verbose in your errors. Be as explanatory, explain as much as you can, because whenever someone faces an error, they need to understand. So here we are failing to read the current directory, and then we're passing the details of the error. Why could we fail to read the directory? Permissions could be an issue, for example. If permissions is a problem, that is a user issue that they need to fix, and it's not related to us. Now, All right, let's iterate over the files. So let's do the following. Range files. And this is how you can loop over, you know, the list of files. The first one is the key. The second one is the value. Okay, remember, don't mistake it. If you pass one variable here, it's always going to be the key. And then you're going to be storing the keys. We don't need that. That's not what we want to do. Now, also one very important thing, we want to ignore some of the files that are not, that we don't want to commit. For example, the dot folder. This is Linux specific, right? If I do it ls-lha, and the H is for hidden, you can see here the dot and the double dot. The dot is the current directory. The double dot is a link to the previous file in the tree. That's how you can understand it. Because again, in Linux, everything is a tree. Files and folders are part of a tree. Dot is a reference to the current item or directory in the tree. Double dot is a reference to the parent directory in the tree. Okay, so we want to ignore these. We don't want to commit those, because then we could go into a endless recursive loop, which we definitely do not want. So we're going to ignore the current directory in all of its forms. We're going to ignore directories as well. Again, just forgive me here. I just want to get to a working state as soon as possible. So I'm going to ignore directories. In the future, we're definitely going to not ignore directories. We're going to go recursively into each one of them and pull out the files and store these files as blobs, right? But for now, let's just do it like this. The second thing we want to do is we're going to open each of these files for reading. So I'm going to open it over here, and then we're going to, if you have an error, also we're going to say failed to open the file, and then we're going to be, before we forget, let's defer the closure of the file. This is a nice feature in Go. And what this does is when we say defer, it will execute file.close as soon as the execution of the parent function finishes. So deferred file.close is located inside the run function over here. So when run function finishes, it will call the file.close. And this guarantees that the file will stay open for as long as we are in the run function. And then when we're done, we're closing it. Remember this, it's very important, because if some other process is trying to also open this file, you might have issues, okay? So you might want to control the file closure in a better way, or yeah, for now this should work. But if we start facing issues with, you know, file reading, we might want to revisit this. The next thing we're going to do is we're going to also create a bytes buffer for the content of the files, because we're going to read them now. Sorry, Copilot and this stuff is becoming a bit annoying. And then we're going to use io.copy, which is going to basically copy the content of the file and store them, or give us a reference to them in our, it's going to copy the content of the file and put it in our bytes buffer, okay? And then if error is not equal to nil, wait, we have something that's not really right. Why is it complaining? What am I missing? Oh, what am I doing? var, this is incorrect. Okay, this is a for loop. Sorry, I apologize about this. It's the end of the day, and the brain is not very fresh. After a long day of going to the gym, working out, doing some reading and other stuff, the brain is tired. But I have to live stream towards the end of the day because I want to try to cover as many time zones as I can. And this is why we do it. Okay, so now I have the content of the file in memory. Fantastic. The next thing we can do is to create our blob, right? So we're going to create a new blob over here, and nope, I don't want the reference for it. And then we say if error blob. And again, for some reason, I thought that the new method should return an error because it could error. It could, maybe. So don't follow me on this one, right? Again, you can see here, new returns an error. It shouldn't. Because new is not doing anything other than just, you know, storing some data in some other variable belonging to the structure. But I thought that preemptively, you know, it might return errors, or we might be doing some more logic there. Maybe we're checking if the content we're passing is empty or not, you know. So that's why we're not doing these checks right now, but I might introduce these checks just for safety. So that's why I'm returning an error here. But just to humor me here, okay? So we're gonna create this new blob, and then what we're gonna do is we're gonna ask the database to store it. And we're gonna do it like this. Over here to pass a reference for this blob, and that's it. This is it. Okay, so here I'm gonna remove this because obviously that's not how it works, and that's what's gonna happen. Now, what we should expect from this implementation is when we run git commit, it's gonna create one object per file. Okay, so let's cross our fingers. Let's hope it works. I didn't write any unit tests. So if this blows up, we might have an issue. So Marwan is saying there is a file path walk dir as an option to walk over the directory. Correct, which we're not going to use right now. We can use it later because we're not going to recursively go over the folders and files. We're just going to keep it simple for now. We just need the list of the files. Yes, Marwan, that's correct. If the constructor is, it's not really a constructor, it's like, you know, this function, if it's doing validation, it can return an error, which is, you're absolutely right. All right, cool. So let's build. Oh, I should have written some tests, but okay. Anyway, g commit. And again, it's not taking any parameters because we didn't implement them. We're probably going to implement one right now because I want to specify a bunch of things, like, you know, the author, who is doing this commit. There's a lot of stuff that's missing right now, but let's see what happens. So commit called, new database was created, and we have the folder. Perfect. Excellent. So if you see here, if we go to .g/objects, you will see that we have the files created exactly as we want them. So we have 2C, and then the rest, 2E, and then the file. So let us see what's actually inside these files. And if you remember from part 1, we wrote this function called zlibd. And zlibd is gonna pretty much, it's a Python script that is using zlib to decompress the content of these objects. So we're gonna use it right now. So I'm gonna say zlibd, and then I'm gonna pass g objects. Let's see, let's look at the first one. All right, interesting. It's empty. It has size 0. We might have an error in our implementation, but let's look at another file. Okay, perfect. No, we don't have an error. So the first file, it seems it's an empty file. The second file is a blob, and then it has the size 369 bytes, and it's our go.mod file. Perfect. Let's look at another file. Let's see if we can maybe get the git commit. Oh, this is our .git ignore. Okay. What else do we have? zlibd /objects. Let's say, I don't know, AD. There's really no indication because these are like SHA-1 hashes. Like, they don't tell me anything about the content. Oh, okay. This is, we cannot decompress this because this is our binary, right? Remember, we built the our project, the Git. So this is the g file, right? Which is a binary, and it's also stored. That's why you shouldn't store binary objects in Git. Remember that, okay? I probably should ignore this in my git ignore, but I didn't add it yet, which is a good reminder, honestly. Oh, sorry. What am I saying? It's in the .gitignore file, but my implementation of g doesn't recognize the .gitignore files. We will get to that in the future. Okay. So again, let's see. zlibd. I just want to find a file that we are familiar with, right? I mean, this already proved the point that our implementation works. Oh, come on. I tried all of them already. Let's see, what else we didn't try. B8. This is our Makefile. We tried this. We tried this. 8a, we didn't try it. Okay, cool. This is our main.go file. Perfect. All right. Well, I mean, the reason why we're not seeing any of these files like the commit.go, anything in the internals, because these are inside directories, right? And remember, we didn't recursively go through directories. So the only files that have been committed right now are the .gitignore, go.mod, go.sum, main.go, makefile, the license file, which is empty. And this is the first one we checked, right? So perfect. We have it working as expected. Let me see over here. Do I need to do anything? Make clean. Let me see. Yep, works. All right. Well, we can move on, actually. I really want to finish this. So I'm probably going to go overboard with time over here, just because I want to make sure that we get the git commit implementation finished. I really don't want to spend another episode on it. So let us soldier through, and let us make sure that it's that's fully implemented. Now, the next step of my implementation is me turning on the light. 1 second. All right, much better. Cool. The next step of our implementation is to write another type of object. And in this case, we're going to get to the point where we need to start storing our tree. And the tree is a representation of our current directory, or any directory that we, walk through or crawl through or commit the files within. So let us start with the tree implementation. And in order for us to implement a tree, we're going to need to implement an object first, which is going to be our entry. And the tree is going to have references to different entries. Okay, so let's implement the entry first, and then we can head over to implement the entries. The tree. We're going to call this entry. Sorry about this. I'm not a big fan of this mode, but yeah, whatever. So entry.go, and then we are gonna create a new type, a new struct, and then this one is gonna also have just the same as everything else, the same as it implements the object interface. So it's gonna have the same thing as our blob over here. Let's put it on this side. Sorry, this is not the content of the blob. Who said that? This is a SHA-1 object ID. Even my comments are wrong. Okay, SHA-1 object ID, and then we will have only the name of the entry, and the name is gonna be pretty much the file name, of that we're referencing in this entry. And then we're gonna create a new entry, which is gonna be done, with the new, and then we're gonna pass a couple of things here. So we're gonna pass the OID as a byte slice, and then we're gonna pass the name. And as I mentioned, validation, it's important. So if name is equal to 0, if length, the length of the name is equal to 0, or the length of the OID is equal to 0. I want neither of these parameters to be empty, so we're gonna return error f, and this is how you define errors. There's really no need to define a new. There are no exceptions in Go, which is beautiful. I love that. And there's really no need to define a struct for errors. Just this, and you're done. At the beginning, I thought like, oh, Go is so verbose, and I have to write everything myself, and why aren't there some of these nice syntactic sugar that I can just use to make stuff happen, you know? But then it just dawned on me, and as I write more code in Go, the more I love it, because it really forces me to think in simpler ways and just implement simpler stuff that are easy to read. No need for these silly abstractions, design patterns, and all of that crap. Just write simple stuff. Of course, it doesn't apply when we're writing like gigantic, ginormous code bases. Like for stuff like this, it makes sense. But yeah, that's part of the reason why I really like Go. So here we're getting the name. Again, a couple of getters and setters for the name, OID, and all of that other stuff. Let's let Copilot do the work. This is exactly why, you know, so it's such a productivity booster. Can you imagine if you had to write every single character over here, including the comments? Thank you very much, Copilot. I love you. And again, I'm not really paid for for this content by GitHub, so I genuinely love this product. All right, cool. Now we have the entry. We're gonna proceed to writing the tree. The tree implementation is gonna be very simple, and it's not gonna do much. It's let's implement it over here. Again, same package. And the tree also is going to implement, let's put this over here. The tree is also going to implement the object interface. So we're pretty much going to have the same functions across the board. And of course, the tree is going to have its own OID. And then it's going to have a slice of entries, right? So the tree is, for now, it's linear. Later on, we're going to do the full Merkle tree implementation. But for now, we're going to keep the tree simple. And it's not really a tree. It's more of a, you know, just a structure on top of an array or a slice. So we're just going to pass the entries over here. And we're going to just store them over here. And we're not going to do any validation, just because it also can take, you know, an empty slice. That's totally fine. Let's add the get OID, of course, and then set OID, of course. Now, the tricky part about trees is how they are being stored on disk. And to facilitate this, because we need to serialize this tree in a way that allows us to store it on disk, right? And this is what the toString function here is going to be doing. So in the previous implementations, like in the entry and in the, did we actually add it to the entry? No, because the entry is not the one that's being stored on disk, right? It's a tree. But for the blob, we implemented toString, right? Which was the string representation of the bytes array. So here, we're going to be doing the same thing, but the toString implementation is going to be a little bit more complex, and I'm going to explain what's happening here. So return a serialized version of the tree, right? Perfect. So Copilot already understood what I want. And all right, it's going to return obviously a string. However, how do we represent the tree as a string? Okay. First things first, we're going to make a copy of our entries. We'll see why in a second. So I'm gonna make a slice of entries that has the same size as my data, and then I'm gonna create a copy of my data and store it in data copy. Okay. Then I want to sort the entries by name. Why do I want to sort them by name? Because I cannot rely on the disk's representation to be sorted. And if you remember previously, the way the tree is represented by Git is a concatenation of all of the different entries together. So each entry is stored as a byte array, and then it's concatenated or appended to the previous byte array. So all of these entries come in a sequence. If you remember from part 1, I showed you in the hex dump that we had the tree type, then the size of the tree content or the entries, and then we had the null byte array, and then we started with the file mode, which was either a regular file or a directory, and then the permission of that file, right? 644, 744, whatever. And then there was the name of the file, which is in this case the name of the entry. And then there was the OID of that particular entry or file, or the content of that file, stored on disk as part of the tree's content. And all of that stuff was concatenated together and stored in the file. So that's what we're going to be doing here. We're going to sort, first of all, these entries. And the way we're gonna do that is by calling the slice stable function, which is gonna take the data copy, okay, which is pretty much a copy of our elements. And why do I do this? Because I don't want to change, I don't want to sort the t.data, right? Because I just want to sort this content and store it on disk, but I don't want to mutate whatever this tree is referencing. That's why I created a copy of that content. Okay, that's why I am sorting the copy. I'm not sorting the original one. So it's gonna take a like a closure or whatever, like over here, which is gonna take 2 parameters I and j, and then it's gonna return a boolean, and then it's gonna compare the name of each of these entries, and that's how it's going to sort them, right? So think of this as map in JavaScript or something else, where it's going to apply this function on every element pair, on every couple of elements inside the slice, until it sorts pretty much everything. Is this the best way to sort? Maybe, maybe not. We will see. We're just going to do this like this for now. Later, we could refactor it to become better, because I'm not really sure how this works. This uses Go's native string comparison, which is a, if I remember correctly, is it a linked list of characters? Probably. And then by using the smaller than operator over here, we can do string comparison. However, I'm not really sure how it applies to names where we have the similar first character. Does it apply to the second character as well or not? I need to look the implementation down in the code of the compiler, but for now, let's just stick to this and keep everything simple. We can make it more complicated later. Now, the next thing we want to do is we want to pack all of the entries into, we want to pack all the entries into a slice, into a byte slice. So how do we do this? And again, remember the structure. The structure is mode space, the name of the entry or the file, null byte array, and then we have the OID, right? And then the next one right after it is going to be the mode, blah, 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 and then so on and so forth, right? But however, you also start with type, and then size, and then also null byte array, and then we move on to append all of these together, right? So this is how the structure is going to look like. We can define it further, but I think you understood the point. And now we're going to have an entry slice. And then we're going to iterate over the entries. Of course, the sorted list. And then what I'm going to do is append the permission, name, so the mode, name, and null byte. And we also need to append the mode in a very particular format. And if you remember, as I showed you in part 1, the format is going to be 100644, like this. This is how it looks like. The first 2 digits are going to be reserved for the file type, whether it's a file, directory, so on and so forth. And then these 4 digits are going to be reserved for the file mode. This is how Git implements it. We're going to stick to its own implementation. Don't ask me why yet. We'll figure it out in the future. Okay? So let us do this. It's going to be entries. We're going to append one of the entries to our slice. Right? So we are taking this entry. We're going to append it here. And then we're going to start constructing the representation. And the representation is going to look like this. We need a byte array of the string representation. And the string representation is going to look like this. 10, and then 04 octal. What this will do is it will first start with 10. And then it's going to make sure that we pad the octal. We make sure that we represent the we pad with zeros the octal number, which is our file mode, and then we add the remaining stuff. And here we need the X for the OID, not OID, sorry, for the null byte, and then we're gonna start filling in the blanks. So the first one is gonna be the G default permission, because right now we stored all the files with that default permission, right? It might be better to get that permission from the entry itself. We can refactor that later and add it but for now we're just gonna stick to this. And then this is gonna be our null byte, and let's just make sure that we balance our parentheses, and I think this is correct. Next, what we're going to do is we're going to append the OID. And I think this gives us what we want. So this is the mode space the name of the file, null byte, and then we forgot the OID. 0, and then F2A. Come on, Copilot. You can do it. Yeah, there we go. And let's assume that this is it. So now we're going to have a byte slice, of all of the bytes from this string representation. And then we're going to append to it the OID, which is already a byte slice. So we just take it, shove it as is. And that's it. We're going to return the string representation of all of the entries which we created together over here. And that's it. That's going to be the toString. That's how we're going to serialize our tree into a format that we can store on disk. And this shouldn't take a lot of work, honestly. It's going to be... we just need to update our git commit and just make sure that we create the tree and we populate it. So let's do that. All right. I know it's long, but bear with me. You can watch this episode later on, the recording on multiple times. Yes, that's a very good point, Marwan. What about the type and size? We need to enter that. You're correct. Absolutely correct. Let's start with this. we need to start with this. Entries append. Yep, that's it. Thank you, Copilot. So it's a tree, and then we have the size, and that's it. So we start with that, and then we append the rest. Thank you. Very good point. All right, cool. Now, we go back to this code over here. Remember, we are still within the loop. So we created the blob, we stored the blob. Now we need to create a new entry for each one of these files, right? Same process, same everything. That's why having an interface is nice, because we can just follow along. So how do we get the file name? Sorry, these need to be flipped. All right, so first of all, we start with the OID and then with the file name. Did we create the tree? We didn't create the tree yet. No, what we want to do is before we create the tree, we want to store these in our entries, which we did not create, right? So we're going to create our entries slice. Okay, and then we're going to append each one of these entries to our entry slice. What's the issue? The result is never used? Yes, sure, fine. We will use it in a bit. Give me a second. All right, next step is we're going to create our tree. We're going to exit the loop, obviously, because we don't want to create multiple trees. We don't just need to create one tree and then add all of the entries to it. And as you can see here, from the new method, we just passed the entries which we collected at the previous step. And again, because we have the tree right now, we can just follow the same process. Copilot already knows what we need to do. We store the tree on the disk, and that's how we're going to have our tree. You see, everything just became much simpler now that we built sort of the important stuff. And now we can do a make build, and then we can run commit one more time. Now, I'm going to open the file here because it's going to show the difference, and we can immediately see once the tree created. So we have two entries that have been created right now. The one that starts with 99, the one that starts with A2. So let's see what's the content of these to check if our implementation is correct. Perfect. So you see here we have the tree. Oh, I should have trusted my my instinct. So Marwan, we were incorrect about our change, right? This needs to be removed. Why? Because the database already appends this for us, so we don't have to do it over here. The higher abstraction deals with this for us. So let's rebuild. Excellent. And let's commit again. Now you will ask me, why are we having these new files created? I will explain in 1 second. So zlibd.g objects 9a. All right, this is our new tree. So internals.read tree, and then this is the size. It's gigantic, I know, but because we have the binary file, right, committed, we can skip it. But I don't want to hard code it for now. And you can already sort of read this in a way, right? But as you remember from part 1, what we used to the way we used to read this database is using hexdump, right? So hexdump -C, and we have the proper reference. So we have the internals.tree, then the size, and then we have the first file mode, which is this for the .gitignore, and then we have the OID for the gitignore, right? And then we have the file mode for the license file, and then the OID for that license file, and then the Makefile, so on and so forth. This is our tree implementation. That's it. I have a couple of things left to do, honestly. but I think it's enough because we are a bit 20 minutes over time. Are we 20 minutes over time? Yes. We are 20 minutes over time, and I think people will not watch this video if it goes on for 2 hours. So what I want to do is stop here. We have a couple of things left, very minor. We want to add the commit object, and we want to allow the commits to be chained. And this way we're going to have the full implementation that I intended to do. Let me think. Is it too much work? Let me see. I think we're almost there. Let's do it. Let's finish it. So let's not waste time. I think you understand how the tree is represented on disk. We have everything else we need. Now we can create the commit object, right? So internals commit.go. I'm gonna sprint in this because you've already seen a lot of this stuff. It doesn't really require a lot of explanation. Okay, so let's do it over here. The commit is a bit more involved just because it has a couple of other elements that we're gonna need to introduce. We're gonna add the type commit, which is also gonna implement the object interface as we mentioned. So parent object ID, you're gonna understand why we need this in a little bit. So this is gonna be parent. It's not gonna be a string, it's gonna be a slice of byte. And then we're gonna need the tree object ID because we need to reference to which tree this commit belongs to. Okay? Again, the entry is not the commit. These are two separate things. Each tree will contain an array or a representation of the files. The commits are stored separately. Now, each commit will also have its SHA-1. Then each commit will have a commit message. You know this already. It's going to have an author, which is not going to be in a string, and it's going to have a committer. And you will ask me, what is the difference between an author and a committer? Well, the author could, so the author could be the author of a commit that involves multiple other committers. And a commit can be co-authored with other people, right? So committer and author might not necessarily be the same thing. So here the author is not necessarily a string. It's also another object which we need to create. So let us create it. And it's a very simple structure. So also package internals, import, oh, sorry, I don't need this. Type author. And this one is not gonna implement the object interface. It's just gonna be very simple, name, email, and then we're gonna have time. Time is gonna be the time of the when this author introduced the change. And this is gonna take as input name, email, and time. And it's gonna set our variables over here. And then we're gonna also have a toString implementation, right? We're gonna expose it because we will need to store this. Sorry, my bad. We will need to store these authors as part of the commit, right? And how is the author stored? If you go and you look at any commit, you will see that the structure of the author element in each commit is as follows. So first we start with the name, and then we have this angled bracket thingy, and then the email, obviously, and then we're gonna have a.time.format, and we're gonna use this specific format, RFC 3399 or 339, because this is the same format that Git uses. Okay, that's how it's gonna look like. This is the author, and now we're gonna need to switch this and this to be authors. Brilliant. Let's go on with the commit. Again, we're gonna create a new one, and it's gonna take a parent, tree, the OID for this particular commit, a message, an author, and an author. Right? And then we're gonna store these without any problems. And then we're gonna also try to create the two-string representation of the commit. So how does it look like? First of all, the parent might not always be specified. So if it's not specified, I want to add a condition where I want because we're serializing here, right? So we're transforming it, translating it into a string. I need to add a condition where we have an empty string for the empty parent. So, oh, come on. If see that parent is equal to nil, which could be its value, I want it to return an empty string. Otherwise, I want it to return the following: parent, and then the value, the hex representation of the parent. Because again, remember, parent is a OID. It's a hash, right? Hexadecimal byte array. It's a byte array that contains the hexadecimal representation. Now, I'm gonna write some comments because I want you to be able to see visually what the sample output could look like. So first, the output will start with the tree, and then it will go on to specify the parent, which is also another object ID, and then author. Amazing. Scott Chacon is the founder of GitHub, if I'm not mistaken. Yes. It's funny. I'm not really sure why it pulled out his name. Cool. So we're gonna call John Doe, Jane Doe, whatever you want. And then the time format is gonna be the following: 05, 29, not 29. What are we? 06, 03, and then 18. What time is it? 9 p.m. 21. This is my local time. We're getting almost 22. So let's put it this way: 22, and then 00 seconds, and then plus 2 hours from GMT. That's how we specify the time zone. Committer, same stuff. And then we're gonna have a couple of empty spaces, and then the commit message over here. Okay, this is how we want to represent the commit. So let us do that. Format.printf, and this is how you can make the best use of Copilot. Just give it the comment. It will do almost all the work for you. Just verifying that everything here is appropriate and it looks correct. Getter for the tree. Getter for the OID. Wait, I don't need this. Function C. Come on. Actually, I need to implement the get type. Honestly, I should do that because my implementation is incorrect. It contains internals.type. It contains the package, which is not what I want. So here, in fact, Copilot is correct. We need to fix it. Let's keep it. I'll probably use it. I need to fix it everywhere else, but that's fine for now. So get parent. And I think this is enough. All right, awesome. Again, the database will easily deal with this, so we don't have a problem. We need to craft the commit over here. However, there are a couple of things you're going to ask me right now. Where do we get the author information? Excellent. So if you remember from Git, whenever you start using Git, you need to do, there's a global configuration, right? So you start by configuring global configuration, you configure your name, you add your email as the author of all of the commits. You can also do that on the level of the repository itself. However, here we don't have the luxury of creating a configuration file yet. So what I'm going to do is I'm going to define a couple of environment variables And then I'm gonna read these environment variables in my command line over here, and we're gonna assume that these define the commit authors. So I'm gonna call these config variables, and obviously I'm gonna rename these and refactor them later, but just humor me here for now. I'm gonna clean it up later. Let me add a to-do here. Read from a configuration file instead, right? This is how it should happen, but for now, let's just stick to this. And the way I want to deal with it is I want to read those. I want to read those variables as soon as I launch my commit. So I'm going to do it over here. I'm going to store these in the variable config, and then I'm going to read these not from the flags. Sorry. 1 second. My notifications have been disabled. Give me 1 second. All right, awesome. So author name, and we're gonna read this author name from our environment variables, and we can do that with with OS get_env, and then we can read this one. We're gonna do the same thing for I'm not sure if you can hear this, but Amsterdam, people come here for drugs and to go crazy. Not everyone, of course, but yeah, sorry, this is lowercase. All right, looks like we have our author information. So obviously once we have the authors, we need to create the necessary objects. And because every commit is done, well, for now, we're going to assume that every commit is done by the same author. We're going to be creating them. So let's create them right now. And because we are committing now, whenever we call this function, we're going to pass time.now, which is more than enough. And we're going to use this author right now, only right now, as the committer, as well as the author of the commit. Okay, so that's how we're going to do it. Let us create the commit, create a new commit, right? And then we're gonna pass the tree.oid. We don't have a parent yet, so we're not gonna pass it. We're gonna deal with this in a little bit. This should be nil for now. And then tree.oid, and then the author, right? We also need to pass another instance of the author. I'm not sure why this is not complaining. Gonna need to pass the author twice. Also, we need to pass the message, which we didn't define yet. The message should be here. Let us define it, because first of all, let me return this error. Let's define it. It's complaining now that message is not defined. So how do we add parameters to our commands with Cobra? We can easily do it with this. It's already added for us, right? So we just need to add one more string variable, and we can do it with commit command flags. There we go. String var p, it takes a message reference, a variable reference, and then this is the long form, this is the short form, this is the default value, which is empty, and this is the description of the flag. Okay, we need to define message, obviously, so let's go up and define it, and this should be a global variable over here. That's how it works. Message, and this should be our commit message. Okay, so now that we have it defined, once you pass it in the terminal, it's going to be stored in this variable over here, and then we're going to pass it on to the other one. All right, what is the complaint right now? Okay, author, committer. Wait. So new, we have the parent, which is nil, the tree. Oh, we need the object ID for the commit, right? And in this case, we have a problem because obviously this should not be part of it. Sorry. I get started also by the new message. Thank you very much for following. All right. We just need to fix the constructor because it shouldn't take on an ID. Obviously here we have a couple of mistakes. See, that's why you need to keep an eye on Copilot, huh? So these are incorrect. And I'm not sure why the compiler did not complain. So the parent is byte array. Well, I mean, yeah, I did not complain because strings are also byte slices. Sadly. Okay, fine. That's what we need. So we need the OID for the parent. We need the OID for the tree. We don't need one for the commit itself because we're going to generate it ourselves. Right? Then we need the message, author, committer. We didn't really generate the... Yeah, the database will generate it and it will use the set OID for it. Cool. Now it should be working fine, which is correct. All right, the next thing we're gonna do is just like we did with everything else, store the commit on disk as well. So let's do that right now, and there we go. And the last piece of the whole puzzle is just to tell. Well, there's also updating the head, but we're gonna skip it for now just because I think it's getting late. The last piece of the puzzle is whenever you commit, right, you print the commit ID as a message. So the way we do it is via this format. This is how it's gonna look like. So we're gonna print it to a standard output, and we're gonna say this is a root commit. Is it correct? Root commit whenever we make the first one. I think so. Okay, anyway, yes, it's gonna be root commit like this, and then we're gonna add the SHA representation, and then we're gonna have the commit message, or at least the first line of the commit message. So let's fix it. Root commit, we can fix it later on. Get OID. Oh yeah, this is correct. And then we will have commit.get message. Did we implement it? No. Okay, let's implement it. Thank you, Copilot. And that's it. That's it. Let's have a look. It compiles. Let us remove the existing folder. Wait, what did we remove? Uh-oh. Ah. Yes, we shouldn't do these operations after a long day. Okay, now I removed the proper directory, and we're gonna be making history right now. So make build g commit -m, making history, first commit. Done. There we go. And we just made the very first commit of our project using our custom implementation of Git. It's not custom, but it's a re-implementation of Git. If you follow my guide, you will be able to get to the same state. Obviously, there's much more to do over here. we need to create the refs file, the head file, which contains the reference to the latest commit. This is also what's going to allow us to chain commits together, so that when we do something like git log, we can fetch the list of all of the commits in a certain sequence, in a tree. We're going to be able to link everything together. So the next episode, we're going to dive deeper into this implementation. We're going to implement the parent concept for the commit. And we're going to start dealing with a lot more problems. We're going to start dealing with staging. We're probably going to start dealing with some branching. We're going to implement the full Merkle tree. We're going to be committing and staging files in subfolders and subdirectories. So we're going to get way, way more involved. I see that I still have like many viewers watching, which is really, really awesome, like after 2 hours. Thank you very much for your dedication. Thank you very much for following. Thank you for all the questions. Thank you for the engagement. And again, if you dropped your GitHub usernames and you subscribed, I'm going to grant you access as collaborators to the repository, where you're going to see the full implementation we did today stored up there. Probably also you're going to get like sneak peeks to what's coming up next, because that's also where I maintain the future versions of the stuff that I want to cover. Thank you very much for watching. I want to wish you a fantastic weekend. Thank you for following these guides. Thank you for your support. And I will catch you next time. Take care.